Okay. Oh, okay. Well, our speaker today is Daniel Carranza, an undergraduate student at the University of Western Ontario. And I should say that Daniel started working on this topic when he was a second-year undergrad and only took basic linear algebra, and somehow checking linearity of some simple transformations was harder for him than working out the details of two adjunctions. So he's one of those people. Yeah, I cannot tell you how impressed I am with everything he's learned and he's done. And so his title today is Formalizing two-adjoint equivalences in homotopy type theory. So Daniel, the stage and the moment are all yours.
Okay. Yeah, I'll be talking about formalizing this notion of two-adjoint equivalences today. You know, homotopy type theory has equivalences, so we'll kind of let's just jump right in. Actually, okay. So this talk is going to have 4 basic sections to it. So first of all, I'm going to talk a bit about formalizing homotopy type theory using lean. The lean theorem prover is what I'll be using today. I'll be introducing sort of our notions of equivalences that we know and love and are familiar with. Then I'll be taking a specific look at the type of quasi-inverses. There's a proof that these things are not propositions, which I will be sort of optimizing and modularizing. And this proof will sort of carry us onto full adjoint equivalences and later full two-adjoint equivalences. And obviously, our final section, which will hopefully be kind of the meat of the discussion, is on two-adjoint equivalences themselves. So just a little bit about this project. This was my USRA project for 2 summers, partly funded by NSERC and partly funded by, Western. So yeah, 2 summers, summer of 2019 and summer of 2020. I worked with 2 of my fellow undergraduates, Jonathan Chang and Ryan Sandford, under the supervision of our very own Chris Kapulkin. Everything that I talk about here is written down in the formalization, which is on GitHub. There is a hot for lean 3 library on there, which has files for equivalences, some results in the hot book, including the optimized proof for quasi-inverse that I'll be talking about, and all this information on two-adjoint equivalences. It can all be found on GitHub under the Gebner Hot 3 library. And hopefully there will be a paper sort of going into more detail on exactly the content that you'll see in this talk. So let's start off with formalizing HoTT. So when I say formalize, I just mean using a proof assistant to sort of check the validity of our proofs. Some proof assistant software that people may be familiar with or may have heard of are Coq and Agda. These are kind of older proof assistants. I will be using Lean 3, which has support for homotopy type theory using the hot for Lean 3 library, which is the library that I was mentioning before. It's maintained by, it has contributions from a few different people, and I think it's maintained by Gabriel Ebner and Floris Van Doorn, who are, good guys they are. So what I want to do right now is I kind of want to demo a bit of Lean 3. I want to show you a bit of how it works by showing some simple, theorems in Lean 3. I want to show off the AP function and naturality of homotopies. So for the AP function, right, we know that any function f we know that we can take paths and move them through functions, right? If we have a path in A, then the function from A to B, then we can, right, this path gets carried through F. So let's show that off how that would work in Lean 3. So this is what Lean looks like, or at least Lean under Visual Studio Code. So just kind of introducing a bit of the syntax here. These are just variables in our context, right? So I have two types A and B, and I have 2 points X and Y in A. That's all that means. So now if I want to define what an AP function looks like, right? I'm going to say for a function f from A to B, I want to define a function that takes a path from x to y and returns a path f of x to f of y. Just so that we're clear, on the left sort of is where all our code will take place, and on the right is the Lean server information. This is sort of what tells us whether our proofs are correct or not, and yells at us if they're not correct. So how are we going to define this? Well, usually it's defined by path induction. So I'm going to assume a path x equals y, and I'm going to use Lean's powerful tactics mode to prove this. The nice thing about tactics is that it tells us exactly all of the assumptions that we have in our context right here. And over here, it tells us what our goal is. So here we want to exhibit a path fx equals fy. How am I going to do that? I'm going to induct on p, which means that our goal is now just a path f of x equals f of x. And that I can just use the good old reflexivity tactic. And there we go. I've defined an AP function. I can sort of check that this AP function works. For example, by using the successor function on natural numbers with a path of 0 equals 0. And we see that if we do this, we get a path that 1 equals 1. One thing to note is that, Lean helps us figure out certain computational rules. So because of the way that AP is defined, right, we know that if we give a reflexivity path as input into AP, then we get a reflexivity path in return. So I can just check that Lean is aware of that, right? The passing refl 0 through the successor function is actually just refl 1, right? Now, if we have two such paths from x to y, right, then we can take a path between, we can take a two-dimensional path between these two paths, right, p equals q, and we can return a path that AP fp is equal to AP f of q. So we can demo that in the Lean real quick. So we call this AP2 for a function f from A to B. Well, first let's introduce these two paths to our sort of context here. So if I have two paths, P and Q, then I want a function of this type, right? And I can actually define this using the AP function itself. I'm going to assume, say, R, a two path from P to Q. And I can just, since APF is itself a function, right, from the path x equals y to f of x equals f of y, I can plug in R and I'll get exactly this type as defined here. Some other things, we know that for any two dependent functions, f and g, we define a homotopy between them to just be this pi type, which basically says they're point-wise equal. That's nothing special. And if we want to take a homotopy and sort of apply it to a point, we're just going to notate that using some subscript notation. And as we know, homotopies have this kind of naturality condition to them, where if you have two functions f and g from A to B that are homotopic to each other, and you have a path between 2 points in A, x and y, then we have that this diagram commutes, right? So we have that f of x is equal to f of y through APF of p, and f of y is equal to g of y, since these two are homotopic. And we have that f of x is equal to g of x, because these two are homotopic, and g of x is equal to g of y by using AP again. So to say that the square commutes basically just says that this path fp concatenated with h sub y is equal to h sub x concatenated with g sub p. If we want to take a look at what that looks like in the lean, right, let's go ahead and formalize that. So we have naturality. So our assumptions are two functions, f and g. This is how we write a homotopy in lean, right? F and g are homotopic. And we have a path that x is equal to y. And we want to show that APF of p concatenated with h of y is equal to h of x concatenated with APG of p. So once again, we're going to use the power of lean's tactics mode. And the way that we're going to go about showing this is we're going to start by induction on p. And here it's actually enough to give a, so this goal here looks somewhat complicated, right? You know, maybe it looks a little scary. It's kind of long, you know, it's like twice as long as the lines in the context. But really, it's not that bad because lean helps us with these computation rules that I talked about earlier, right? We remember that passing refl through the AP function just gives us refl back. So really, this is saying refl concatenated with h of x equals h of x concatenated with refl, right? And we know that refl concatenated with anything is just the same thing. So an example of that is refl f of x concatenated with h of x is equal to h of x. In lean, the name of this proof is just idpcon for h of x, right? And the other nice thing about lean is that because of the way the path induction is defined, h of x concatenated with refl x is actually just reflexively equal to just h of x. And so what that means is that this new assumption that we have here, right, that refl f of x equal concatenated with h of x equals h of x is actually enough to just finish the entire thing. So that's kind of nice. So aside from demoing things in lean, I want to talk about things that we're going to be kind of using a lot throughout this proof. We have an equivalence induction lemma, which says that, so basically if we have an equivalence f from a to b, and we want to prove something about this equivalence, right, it suffices to prove it in the case that our f is just the identity map from a to itself. That's essentially what equivalence induction is. The way that you'd go about this comes to us from the univalence axiom, right? Since an equality between a and b is equivalent to, an equivalence from a to b is equivalent to an equality from a to b. And we know that for path induction, right, if a is equal to b and we want to prove something about a path, then we just assume it's reflexivity. And of course, reflexivity between two types corresponds to the identity equivalence between those two types. But that's fine. This is something that we're going to be using. This essentially, one thing I should say is that this essentially packages all of our uses of univalence for us. So all of the uses of univalence that we're going to be using throughout this discussion are essentially packaged in this lemma of equivalence induction. And the other lemma that we're going to need is this based homotopy induction, which says that if we fix a function f from a to b beforehand, then it turns out these sigma types are contractible, right? This is sort of the type of functions that are homotopic to f. This parallels this parallels a similar result for paths, right? If you fix like some x in a type A, then you know, the type of elements of A that are equal to x is well known to be a contractible type. And so here we're just saying that the same thing holds for homotopies as well. And this essentially packages all of our, this comes to us from function extensionality, right? Because a homotopy between f and g is equivalent to a path between f and g. So this lemma essentially packages all of our uses of function extensionality for us, which is kind of important. So now we're ready to talk about an equivalence of types, right? So first thing we're going to define is we're going to define what a quasi-inverse is. For a function f from a to b, we say f has a quasi-inverse, essentially if it has an invertible map in the way that we would expect. Constructively speaking, the type of quasi-inverses is a triple. It consists of a map from B to A and two homotopies that say that these composites are homotopic to the identity. This is a great place to start off for if you want to. This is a great place to start off if you want to define what an if you want to talk about what an equivalence of types might be. At least I think it is, or I would have thought it would be. If you had asked me, right, when two types, so if you had sort of locked me in a room, right, and told me, you know, you can't come out until you tell me when two types are equivalent, I would call the cops. But if I couldn't call the cops, if you took away my cell phone, then I might sit there for maybe a day, a week, or a month, and I might have come up with this definition, right? Two types are equivalent if there is an invertible map between them, right? And so because this is something that I could have come up with, it makes sense that this definition is no good. This definition in particular is not a proposition, which is something that we'll talk about more later. But instead we fix this definition, as we know, by defining well, there's a few different ways to fix this definition. But it turns out that the way that is used in Lean is we use the notion of a half-adjoint equivalence. Now, a half-adjoint equivalence for a function f has all of the same data as a quasi-inverse, right? So it has an inverse function and two homotopies, but we ask that there's this additional compatibility satisfied here. This compatibility, for those of you that are familiar with, you know, a bit of categorical goodness, comes to us from one of the triangle identities for an adjunction. And if you are familiar with adjunctions in category theory, then you might know that there are two such triangle identities. And so it turns out that there are also two such definitions of a half-adjoint equivalence. So we define a left half-adjoint equivalence to, again, have the same data as a quasi-inverse, but instead we ask for the other triangle equality to hold. One sort of small technical point that I'll take note of now is that I've drawn this diagram here to sort of mirror the typical diagrams that you'd see in category theory. But because of the way, because we have eta going from GF down to id, if you're looking at these types, you would actually expect eta to be going in this direction. Just a small technical point, but I thought I would make note of it. So how do these types interact with each other? Well, it turns out that from any one of these, you can get to the other two. It's very obvious that if you have a half-adjoint equivalence or a left half-adjoint equivalence, you can just discard the triangle identity you asked for, and you land back at a quasi-inverse. So what's interesting is that you can promote any quasi-inverse to a half-adjoint equivalence or a left half-adjoint equivalence, and that you can go back and forth between these two types of equivalences. Not only that, these two types are propositions, as we know, and which makes them equivalent to each other, right? There's a map back and forth between them, and they're propositions, so they're equivalent. This kind of summarizes everything that we know about equivalences right now. This is for hot book readers. This would be the first little bit of chapter 4 in the hot book. And so now I want to talk specifically about quasi-inverses. I'm going to give a proof that quasi-inverses are not propositions, and this proof is different from the proof that you'll see in the hot book in ways that I'll make note of later. But in order to prove that quasi-inverses are not propositions, I'm going to, one thing I should say, by the way, is that I don't know if anyone has any questions, feel free to like speak up and interrupt me or anything. But I'm going to show this equivalence. I'm going to start off by, I'm going to show that quasi-inverses are not propositions by showing off this equivalence. And the way I'm going to go about, doing that, right, is I'm going to assume a function f, which is an equivalence, and I'm going to use I'm going to start off with equivalence induction, right? So by equivalence induction, it suffices to assume that this f is just the identity, right? And if I just have the identity, then writing out what the type of quasi-inverses means for the identity, I get exactly this type here. What I'm going to do is I'm going to take this product and I'm just going to write it as a sigma product. We know that Cartesian products are just a special kind of sigma product, so we can definitely write this. And now what I'm going to do is I'm going to take advantage of sigma associativity to move eta down with G, and I get a type that looks like this. And so now if I look at this type, right, I see that this is actually a contractible type using our based homotopy induction. And so I can simplify this whole expression. This is a contractible type, and notably the center of contraction for G is going to be sent to the identity on A. So after I simplify, I end up with just this, right? Plugging in the identity here. So I get a homotopy from the identity on A to the identity on A. And if I just remember that homotopies are a special kind of pi type, I get exactly the equivalence that I was looking for. So just to sort of recap, what we're doing here is we take this type, and essentially what we want to do is we want to pair off these two pieces of data. We want to pair off the inverse with one of the homotopies. And what happens is that we have this leftover homotopy that's going to end up being this type that we're looking for. And this is why it's not a proposition. The reason why I say this proof is different from the proof in the hot book is because the hot book does not use based homotopy induction. What it does instead is it calls function extensionality directly to turn these homotopies into paths between functions. After that, it sort of contracts them using our sort of based path induction in the same way, and then calls function extensionality again to turn a path id A to id A back into a homotopy. So here I say it modularizes the proof that's in the hot book because what we've done is we've used this based homotopy induction lemma to sort of package up and clean up our use of function extensionality. Right? That's fine. I say that this is good enough to show that it's not a proposition because in particular, right, if I just take the identity on S1, this is a perfectly fine equivalence, right? Then the type of quasi-inverses on S1 is the circle, by the way. Then the type of quasi-inverses for this function, it turns out, is not a proposition. By our previous theorem, it suffices to just give it suffices to show that this type is not a proposition. The way I'm going to do that is by constructing two non-equal elements. We know that pi1 of S1 is equal to Z. So if we have one such element that sends base to, so we want, if we have one such element that sends the base to refl base, right? Refl base is a proof that base equals base. And I have one that sends it to the loop on S1, which is also a type that base equals base. Then since we know that refl base is not equal to loop, we know that these two functions can't be equal to each other, which means that this type is not a proposition. And so this proof sort of illuminates why the half-adjoint equivalence fixes this type. The way that we're going to show as a proposition is we're going to assume it's inhabited and show that it's contractible in that case. So we're going to assume an inhabitant. And we're going to write out, again, we're going to use equivalence induction to just write out what this means. From the previous proof, we know that we can package off G and eta. So I'm going to do that right away. I'm going to contract G down to the identity. I'm going to contract eta down to refl x. And I get a type that looks like this. We remember that refl on AP is just refl. And we know that we remember from based homotopy induction that this is a contractible type, right? It's a contractible type because epsilon is a homotopy, and a homotopy is just a kind of dependent function, right? So really, this is the type of functions that are homotopic to the reflexivity homotopy. So we know that half-adjoint equivalences are propositional types, right? If we wanted to prove that left half-adjoint equivalences are also propositional types, then it's a very similar proof. Both triangles kind of boil down to the same thing. So we know that appending either triangle fixes the type of quasi-inverses. But it turns out that if we append both triangles, something kind of, apply based homotopy induction. It turns out that if we put both triangles together, then we get not a propositional type again. So we're going to define the data of a full-adjoint equivalence as just, this is the same data for our quasi-inverses and both of our triangles. And it turns out that this type now is equivalent to a function that looks like this, to a type that looks like this, sorry. The way we're going to do that is by a very similar method. We're going to use equivalence induction to reduce it to the case that we're working with the identity. In that case, writing out the data of a full adjoint for the identity, we get this type here. And again, in the previous proof, we knew that we could pair off G with eta and contract them down. G contracts to the identity, eta contracts to reflexivity. So I get a type that looks like this. Again, simplifying, refl on AP on refl is just refl. So I can simplify that down real quick. And then if I look at this, I'm going to carry out a similar set of tasks that I did for quasi-inverses. I'm going to take this product, I'm going to write it just as a sigma product, which I'm allowed to do. I'm going to use sigma associativity. And after I use sigma associativity, if I stare at this, again, I'm going to see that applying this type is contractible by based homotopy induction. Again, this is actually the same type that we saw in the half-adjoint equivalence. So we know that this is a contractible type. And after we contract, we're going to get something that looks like this. I'm going to once again write that AP refl is just refl. So I get sort of a refl is homotopic to refl. And if I just remember what homotopy means, then I get exactly the type that I'm looking for. I say that this suffices to show that the data of full adjoints is not a proposition. This time, I'm going to take my equivalence to be just the identity map on S2. S2 is the sphere. As we know, the sphere comes with the sphere is inductively defined by a point base and a will be in a cell that says refl base equals refl base. By our previous theorem, it suffices to show that this type is not a proposition. And we know that pi2 of S2 is Z. So if we just take two such elements here, one that sends base to refl base, right? Refl base is a proof that refl base equals refl base. And we send the other to our cell that we just described. Since we know that refl base is not cell, we know that these two objects are distinct from each other. So this type is once again not a proposition.
Can I ask a question, Daniel?
Yes.
So you've used equivalence induction a bunch of times, and that relies on univalence.
Yes.
And univalence relies on a definition of what an equivalence is.
So yeah, that's a fair point. I think that the way that the HoTT goes about doing that is in chapter 2, very early on, they introduce what an equivalence is, and they sort of pick a suitable definition without fully explaining why. So I suppose the answer to this would be, I suppose the answer to this would be to we pick whatever definition of, we pick a suitable definition of equivalence. So say you can define the type of equivalences, right, to be these half-adjoint equivalences, and then sort of define all of your favorite equivalences, including univalence. And after we do that, sort of we can talk a bit more about additional properties of these equivalences, is I suppose how you'd go about resolving this.
Yeah, because for example, I think if I chose bi-equivalences, or sorry, not bi-equivalences, the quasi-invertibility that you started with, and I define univalence with that, I think I'll be able to prove that that's a proposition, but I'll also be able to prove that it's not a proposition. I mean, it won't be consistent. But so if you state a definition of equivalence and then assume univalence, you'll always be able to prove that definition's a proposition, because you can translate it to equality, and you get the appropriate based path space. So it's a very delicate issue, actually.
I see. Yeah, fair enough.
But I don't think Daniel was using univalence. Like, he stated specifically the equivalence induction bit, which follows from univalence, right? But univalence per se is never used. So,
well, you need univalence to prove that.
No, but you can take equivalence induction as an axiom, and it follows from univalence, but you don't need to use you don't need to use univalence. You can just use equivalence induction.
Right, but then you have to choose which kind of equivalences you state equivalence induction for, and you get the same problem coming up. So, and you used multiple notions of equivalence, and you used equivalence induction for all of them, rather than translating to one that you state univalence induction for. So, I think there's a little risk of circularity if you're not careful in these arguments.
Yeah, no, I think that's a fair concern. I don't know.
Yeah, it's okay. It's just a comment. I mean, I think, you can organize it all in a way that's all self-consistent, but I just wanted to point out that it requires a little bit.
Yeah, so it seems to me that the way you resolve this is with a bit of foresight beforehand, knowing that you're picking a good definition of equivalence in order to get a consistent, in order for everything to work out, and for you not to have any inconsistencies in your theory.
Right. I mean, but Lean makes this choice, right? The library makes this choice for you already. So. Yeah, and it's stated using half-adjoint equivalences. Just to answer the question once and for all. It is resolved this way.
Okay. Yep. So continuing onwards. So now, right. So we know that these full-adjoint equivalences are not propositions, right? But maybe, in the same way that quasi-inverses could be fixed by attaching a triangle identity to them, right? We can ask, is there some kind of additional coherence or compatibility that we can attach to the data of a full-adjoint equivalence in order to, once again, get a propositional type? If such a type exists, we would expect that this is sort of the two-adjoint equivalence that we are after. And so one thing we can do is we can sort of talk about what properties we would expect out of such a two-adjoint equivalence if it exists. So far, our map of sort of logical implications or maps between these types looks like this. We know that this is the same map from before. We know quasi-inverses can be promoted to half-adjoint equivalences. These two types are propositions, and they're equivalent to each other. And we know that adjoints, full adjoints, obviously we can get from a full adjoint to either half adjoint just by discarding a compatibility. So if we expect there to be a compatibility we can attach to full adjoints, mimicking the sort of step from quasi-inverses to half-adjoint equivalences, we might expect a map, a sort of landscape that looks like this, right? We have a notion of some kind of half two-adjoint equivalence, which is a proposition, which attaches an additional coherence. In the same way that half-adjoint equivalences have two possible coherences we can attach, we might expect that there are two possible coherences we can attach to the definition of a full-adjoint equivalence. We would really hope that these types are propositions. We would hope that we can promote the adjoint to the full adjoint to either one. And we might even expect that if we had two such coherences, that attaching them both would give us a non-propositional type again. So this is kind of what we would expect out of a half two-adjoint equivalence, right? So let's just try and build one, right? Before, the way that we build one is by, by saying, right, by asking for a homotopy between, so the right triangle, for example, for the one in the half-adjoint equivalence, asks that f eta be homotopic to epsilon f. And the left triangle asks that eta g be homotopic to g epsilon. So let's try and do the most obvious thing, which is just to stick g or f on our sort of tau. And oh, I guess I never actually. So one thing I will say is tau is the, I'm going to call tau the right triangle here, right? So tau I'm going to say is the type f eta homotopic to epsilon f. And theta I'm going to say is the homotopy eta g to g epsilon. So if I have these coherences, tau and theta, these two triangles, I'm going to stick g and f. There's 8 possible combinations, but of those 8, 4 actually makes sense. G tau, tau g, f theta, and theta f. And so one thing I might try to do is I might try to just pair 2 of them off together. So one possible candidate for a coherence is that g tau is homotopic to theta f, right? This is the thing that I would have tried, and that I did try to find this missing coherence. And this again is bad. This does not type check. Why does it not type check? Well, if we look at the types of g tau and theta f, right, g tau says that g f eta is homotopic to g epsilon f, right? But theta f tells us that eta gf is homotopic to g epsilon f. So what we're missing is we're missing a path between these two things. If we want a coherence that involves these building blocks, we're going to need a additional sort of path or homotopy between these two objects. And so it turns out that we're going to define such a homotopy, right, for an H that looks like, say, eta, right? Eta is GF is homotopic to id, but in general, these are any two functions, right, G and F. We have this homotopy between HGF and GFH. This comes to us from just drawing the right naturality square. Right, naturality gives us that this square commutes, and we note that, right, so HGF composed with H is equal to GFH composed with H, and we can whisker out H on either side to just get that HGF is homotopic to GFH. And so now that we have such a now that we have this missing coherence, we can define the type of a half two-adjoint equivalence. The data of a half two-adjoint equivalence has all of the definition has all of the stuff in our full two-adjoint, our full-adjoint, right? It has our G, our function, our two homotopies, and our two triangles. And we ask that this coherence on eta concatenated with g tau is homotopic to theta f. Those of you who are familiar with category theory may recognize that this is coming to us from the two-adjunctions. Two-adjunctions, the identities that a two-adjunction has to satisfy are the swallowtail identities. And again, there are two such swallowtail identities. So we have two such notions of a half two-adjoint equivalence, right? A left half two-adjoint equivalence is going to have all of the same information from our full-adjoint equivalence and the other swallowtail. So now we want to sort of prove that all of these maps that we talked about in our landscape of equivalence types, we want to show that these maps actually exist. And the way that we're going to do that is we're going to start off with a little lemma here. We note that for a function f from a to b and the data of a left half adjoint, right, that's a g eta. We're going to fix f, g, eta, epsilon, and theta, theta being our left triangle, right? And once we fix all of those things, it turns out that the sigma pair of our right triangle with our right swallowtail is contractible. And the same thing goes in the other direction. If you fix f along with the data of a half adjoint equivalence, which is g, eta, epsilon, and tau, our right triangle, then the sigma pair of our left triangle with our left swallowtail is going to be contractible. I'm not going to go over these proofs at the moment since that's kind of it's not really what I want to focus on. But these proofs are, these proofs are interesting. If you want to ask me about them later, go for it. So one thing that is immediately obvious if we have these two results are that we can promote a left half adjoint to a half two adjoint, and we can promote a half adjoint to a half two adjoint to a left half two adjoint. And the way that we're going to do that is we're just going to take our missing coherences to be the center of contractions from before, right? In our half adjoint left, we have, f, g, eta, epsilon, and theta. So in order to get a tau and a right swallowtail, we just need to take the center of contraction. And the same thing for our other adjoint equivalents. And so notably, if this is true, then we can definitely promote a full-adjoint equivalence to a half-two-adjoint equivalence, because an adjoint equivalent, because a full-adjoint equivalence has this data of a left half-adjoint or a right half-adjoint. So you can discard whichever coherence you like and use the respective promotion. So the last thing we want to do is we want to show that these types are indeed propositions. I'm going to show that the half-two-adjoint is a proposition. If I want to show that the left half-two-adjoint is a proposition, it's going to be a very similar proof, so I'm only going to cover one of them. The way I'm going to show that this is a proposition is the same way I showed that the half-adjoints are a proposition, or similar. I'm going to start off by assuming an inhabitant, and then I'm going to show this type is contractible. I'm going to write out just the type of half-two-adjoint equivalences, right? For a function f, it looks like this. And what I can do is I can interchange theta and tau. I'm just going to swap the order. That's all I've done here, and this equivalence definitely holds. And then I'm going to take g, eta, epsilon, and theta here, and I'm going to package them all together to get a left half-adjoint equivalence, right? These four things all form the data of a left half-adjoint equivalence for f. And since we know that left half-adjoint equivalences are propositions, and we know that they're inhabited, right? Notably, f is a half-two-adjoint equivalence, so it's definitely a left half-adjoint equivalence. Since we know it's a proposition, and we know it's inhabited, we know this type is contractible, right? We don't necessarily know what the center of contraction is. I mean, you could find out, but it doesn't really matter what the center of contraction is. So I'm just going to, what matters is that we can simplify this type down. And I'm going to substitute my, I'm going to call these, this should say h eta, by the way, small typo, but let's not worry about it. I'm going to contract g, eta, epsilon, and theta to hg, h eta, h epsilon, and h theta. And then after I do that, what do I have? I have a sigma pair, right, of a right triangle with a right swallowtail. That's exactly what this is. And we just said that by our lemma that this type is contractible, right? And so that means that once we apply this lemma that we have, we know that the type of half-two-adjoint equivalences is a proposition. And so we're golden. We've shown that we can promote an adjoint, a full adjoint, to either half-two-adjoint. We've shown that these types are propositions. If we want a map between our half-two-adjoint and our left half-two-adjoint, we can just discard down to a full adjoint and then promote again. So that's not a problem. So now, and in fact, we have something even better. We have that, we now know that these maps, we can go from a half-adjoint to a full adjoint, right? We said that the half-adjoint can be promoted all the way up to a left half-two-adjoint. So we can promote to an adjoint along the way and then promote up. And the same thing for left half-adjoint equivalences up to half-two-adjoint equivalences. That's great. Now the only thing that's left is to show that this full two-adjoint equivalence is not a proposition. And so we're going to define, so we define the full data of a full two-adjoint equivalence to be exactly what you expect, right? We put both swallowtails together. And in order to show that it's not an equivalence, we're going to exhibit this equivalent. That's not a proposition, sorry. We're going to exhibit this equivalence here. We're going to start off in the same way. We're going to use equivalence induction. To assume that f is the identity, after we do that, writing out what this type is, it's this, massive thing here. Let's not worry about it too much because we know from the previous proofs that we can pair off G and eta together, right? We pair them off, we contract them. And we can pair off epsilon and tau together, right? If we remember from the proof for a full adjoint equivalence, we paired these two off and contracted them. After we do that, G is going to go to the identity, eta and epsilon are going to go to refl x, and tau is going to go to refl x. And then I end up with a type that looks like this. So once I have a type that looks like this, I'm going to take this sigma. I'm going to take this product. I'm going to write it as a sigma product. I'm also going to take this time to simplify identity on theta down to just theta. I'm going to use sigma associativity to bring this bring these two together. And now, if I stare at this type here, the type of U, I know from based homotopy induction that once again, this is a contractible type. Theta is going to contract to just refl x. And so after I do that, I get this type. And once again, I unfold this definition and I get exactly the equivalence that I'm looking for. So now I say this is good enough to show that it's not a proposition. This is going to be, again, the exact same gambit, right? We're going to show that it suffices to show this type is not a proposition. This time I'm going to pick the identity on S3. We know that pi3 of S3 is Z. So we just need one of these to send the base to refl base, and the other to send it to our cell, which in S3 says refl base equals refl base. And since these two are not equal to each other, obviously this type is not a proposition. I'm going to take a moment to show off sort of what this formalization looks like in the code. So here is, well, let's start here, right? Here is the all of formalizing everything for quasi-inverses, half-adjoint equivalences, and full-adjoint equivalences. It looks, it looks like this. The thing that I kind of want to draw attention to is this modular proof here that we presented, that full-adjoint equivalences on F are equivalent to just pi x and a, such that refl x equals refl x. This proof goes almost exactly as we expected it to go in the slides. We first apply equivalence induction. That's what this says. And then what we're going to do is we're going to use this lemma here, right? We call associativity of sigmas, and then we contract G and eta together. And then what we're going to do is we're going to write the product as a sigma. We are going to use sigma associativity, and we're going to contract, it was epsilon and tau together. And then we just are left off with this theta homotopy that goes. And the reason why I want to highlight how simple this proof is because if you don't modularize if we don't modularize this proof of quasi-inverses, and if you try to sort of, use function extensionality sort of directly, then this proof, it turns out, would look a lot longer. This is about, I think, 20 lines. And starting from the definition of a full adjoint equivalence, right, I need to use, so I want to prove the same thing, right, that the full adjoint equivalences on F is equivalent to this pi type here. And the way it's done here is it uses, let's count 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 9, 10, 11 lemmas. And this whole thing is, I believe, about 60 lines. So this is why the modularity down in quasi-inverses is so helpful. using function extensionality to turn these homotopies into paths, the way that it's done in the hotbook, for full adjoints will give us a much longer proof and requires sort of a lot more work. This sort of eliminates a lot of the work that needs to be done, and a lot of these equivalences, like some of these lemmas are not easy. Some of these lemmas are harder than the stuff that we had to do here. And so this is sort of the power of modularizing our proofs when it comes to formalization. Right, this is sort of in summary, right? We modularize. So obviously we have a definition. We have this nice definition for two-adjoint equivalences. We demonstrate kind of how their modularity and quasi-inverses helps us going forward. In total, the formalizing all of the content that is in this talk is about 528 lines, and it's on GitHub, as I said before. If you go to the library, then you can see sort of the 3 files that are contributed under our collective name, our being the team that I mentioned at the beginning with Jonathan Chang, Ryan Sandford, and our supervisor, Chris Kapulkin. Once again, we hope to have a paper sort of that really goes into detail on this formalization a little bit more. And the last thing that I want to say is that, you know, if you are sort of very adept in your higher categories and the like, then, you know, maybe nothing here is surprising. You know, you might say that there's some sort of easy semantical argument, you know, using some kind of, you know, whatever model category makes you feel like, and you can very easily show everything that we, you know, spent our time here showing. And that's okay. Really, the point here is about formalization, right? We want to show how you can, you know, take these proofs and you can take this definition of two-adjoint equivalences and formalize it using a proof assistant, right? Using Lean 3 and, you know, have the computer check it for you. And putting this in a way that a computer can understand, right, is definitely not, you know, it takes 528 lines to do it. And so it's okay that it's not surprising, basically. And that about, I think, wraps up everything I want to say. So thank you for your time. And,
right, well, thanks, Daniel. That was great. So we're going to do silent applause. So please don't unmute your mic, but we're all clapping. Okay. So yeah, I have one quick comment before I open the floor for questions, and that is Daniel made it all sound completely trivial, but I think that the thing that he showed at the end, how much simpler things gotten by modularizing, is exactly the whole point. It's one of those things like energy versus entropy. It would be a huge mess, but like there's a brilliant insight how a small change can make everything absolutely straightforward. And so, yeah, it may look easy, but it actually has a lot of brilliant insights. So now I'll open the floor for questions, comments, and otherwise.
I'll make a comment. So there was a post on the Homotopy type theory mailing list on Sunday, which proposed a different definition of equivalence, which has some really nice properties. In particular, it's definitionally associative, and the identity map is definitionally a two-sided inverse, or sorry, two-sided identity for composition. Just thought you might find that kind of thing interesting since you've been thinking about all the different definitions, and there are ways to tweak them to get even better properties sometimes, which is kind of cool.
I'll take a look. I had no idea, so I'll definitely take a look. I've spent a lot of time staring at these equivalences. Thank you.
All right, anyone else? Questions, comments? Well, in chat we have, I'd imagine that's a it's more of a comment. Great talk, Daniel.
Thank you, Udit.
Okay. Anything else? I agree that it was a great talk. Okay, so I think we should thank Daniel again. So please join me in applauding. Okay.